In the previous class, we started the discussion on parallel plane waveguides, which is nothing but a pair of conductors kept parallel to each other, and we saw how we can guide a wave in between those two conductors, which is filled with some dielectric. So in particular, we looked at something called as the transverse electric, or the TE suffix M mode of propagation. So that happens when the field is incident on any of the conductor boundaries obliquely, and the polarization of the wave is vertical. That means the electric field vector is coming out of the plane of the paper. So when that happens, or rather we had said that let the waveguide axis be something like this. We had defined this as the z-axis, this as the positive x-axis, and the y-axis is coming out of the plane of the paper. So therefore we had sort of three field components in between the two plates, that is Ey, Hx and Hz. So we have derived that in terms of the mode number m and the other parameters, like for example, if the distance between the two plates is d, then we get the following field expressions. Let's just write them again. This is the Ey component. Hx looks like this. And Hz, the last but not the least component. So what we had seen in our analysis in the previous class, this quantity m lambda by 2d is equal to cos of theta, where theta is the angle of incidence on any of the plates. So we saw that we can vary m width by changing d, or if you want to fix d, then m can be varied by changing theta. So, and most of the time this is what we do. So we essentially vary m by varying theta. This is what is important. So now let us take a very special case. Let us take a special case and put m equals 0. Now this might sound something very strange, because up until the previous class the smallest value of m that we had started with was 1, and now I am saying let's put m as 0. So supposing I am varying m by varying theta, that can be done. So if m is equal to 0, that means cos theta will be 0, which implies theta is pi by 2. That means the angle of incidence now becomes so large that we can say that the wave is incident on the surface by sort of grazing it. So it is both incident and not exactly incident. So what happens now? The moment we have m equal to 0 and we substitute that in these field expressions, we see that all the three fields, which three fields? Ey, hx and hz. What happens to those fields? The moment you put m equal to 0, the sine term becomes 0 and this term also becomes 0. So all of them identically become 0. That means it just cannot happen. That means it just cannot happen. You cannot sustain a wave which is incident on either of the conductors with an angle of incidence of pi by 2 when the field is vertically polarized. You cannot sustain the TE mode of propagation. So that means talking about let's show this as EY, and obviously the H will be here. So you cannot sustain a wave which is vertically polarized and striking either of the conductor surfaces with an angle of pi by 2. Now this is the mathematical part. We saw that the moment we put m as 0, or if you want to put theta as pi by 2 in the expressions which have theta, that is, if you recall, we had represented these forms by eliminating theta. If you go back and if you put theta as 0, you will get the same thing. Sorry, theta is pi by 2, not 0. So now this is the mathematical explanation. But what is the actual reason why we cannot do this? What is the actual reason why we cannot do this? So the reason is again the boundary conditions. So supposing I have EI vector which is coming out of the plane of the paper and it is trying to be incident on this surface. So now what is going to happen is that at the surface also of the metal, the EI is going to have, or it's going to be a tangential component because it is grazing the surface. So as we know, the tangential component of EI, it must obey the boundary condition that the E1 in medium in the dielectric must be equal to 0 at the point of incidence. So that is why we have a reflected wave which is generated. And the magnitude of this wave is exactly equal and opposite to the magnitude of the incident wave field. We saw this. So we had proof that EI0 bar is exactly equal to minus ER0. Now this is what is generated. But now, suppose we are trying to launch a wave like this. That is when theta becomes pi by 2. This is theta. So in this case, we are assuming that let this wave have some field, electric field EI, which is vertically polarized. So when it is grazing the conductor boundary, it must obey the boundary condition. So therefore, EI must be 0. So the moment EI becomes 0, there is nothing which can sustain the magnetic fields. There is no concept of reflected wave now, because the discussion we are having is now contradicting itself. we are saying that we are launching the wave grazing the surface where it is not exactly incident, and the only thing that can sustain the field is if we have an equal and opposite field which is generated, reflected, and that is not happening. This wave is trying to travel by grazing the surface. So therefore, the boundary conditions take over and they dictate that the moment the wave tries to travel like this, well, in this case, the electric field must die down to zero. So the moment the electric field dies down to zero, all the other magnetic fields, that is Hx and Hz, also become zero. So therefore, Te with the mode of 0, that means m equal to 0, cannot sustain. So for transverse electric case, the minimum possible value of m you can have is 1. So m can be more than or equal to 1. This is okay. This is okay. So this is something which you should know. Now, let us look at the other thing, the other way of propagation, which is called as a transverse magnetic propagation. Or TM propagation. Now, when the propagation was transverse electric, the electric field vector was perpendicular to the plane of the paper. Now, in case of transverse magnetic, the electric field will lie on the plane of the paper, and it is the magnetic field which will be perpendicular to the plane of the paper. So therefore now the wave that is being incident on either of the conductors must be horizontally polarized. So now let us assume that. So let's say that a wave is incident like this. So this is the magnetic field vector. So this I can write as Hi. So therefore Ei will be like this. So that's why to maintain the direction of propagation, the electric field vector should be like this. This is theta. Let this be again d. So we have already proved this before. Now there will be three field components. This is z-axis, this is the x-axis, and this is the y-axis. So now the magnetic field component will exist, that is Hx. Along with that, there will be two electric field components on the xz plane. Sorry, this will be Hy. I'm sorry, because the magnetic field is along the y direction. So we will have Hy. Now since the electric field vector is lying on the xz plane, it will have two components, that is Ex and Ez. So these are the three components. So you can very easily prove using direction cosines and other things that the total electric field in the dielectric, because of the reflections and the incident wave, would be something like this. Ex is this is something you can prove. You can also prove that Ez is 2j Ei0 cos theta sin beta x cos theta times this very factor, which indicates the propagation along the z direction, and Hy is 2ei0 by eta cos beta x cos theta e raised to minus j beta z sin theta. So if we now apply the boundary condition, we can again consider the tangential component of the E field. That means the boundary condition dictates that the z component of the electric field that is tangential to the z axis, that must be 0. So if I put this Ez as 0, what will I get? I will need that this beta x cos theta must be equal to some m pi, very similar to what we had proved last time. So even if we now put some x is d, then we get d is m lambda by 2 cos theta, or cos theta is m lambda by 2d. So it's a very similar result what we got in the case of the transverse electric. So therefore even here let us put the suffix or subscript m, that is small m, which denotes the mode of the propagation. So now if we want to represent all the three fields without using theta, just like how we did for the transverse electric case, we will get Ex is this 2ei0 this is a sine term, so it will be 1 minus cos square, the whole under root, this is Ex, then comes Ez, which is 2j ei0 m lambda by 2d sine m pi by d x times e raised to minus j beta z 1 minus m lambda by 2d whole square. And last but not the least, we will have Hy, that is 2ei0 by eta cos Is that fine? Yes. Now, if m equal to 0. Now, if m becomes equal to 0, what happens? Immediately, I can say that Ez becomes 0. Immediately, I can say that Ez is becoming 0. But what about Ex and Hy? They will not be 0. So Ex will be 2ei0. This will become a 1. This will stay as 1. And we will get this times e raised to minus j beta z. And Hy will also not be 0. This will be 2ei0 by eta times e raised to minus j beta z, as this term will become 1. And so will this root term. Now we notice something very interesting. Unlike the case of Te, where m being made 0 means that all the fields vanish. In case of Tm, the transverse magnetic mode, if we make the small m equal to 0, that is like saying the angle of incidence theta is pi by 2. The angle of incidence theta is pi by 2. Only one of the field components die out. The other two exist in a hale and hearty manner, and what we can see over here is that mod of the Ex divided by mod of Hy is actually equal to eta. So therefore, the Ex and Hy, they essentially constitute a wave which is flowing towards the z direction. So how can we draw this now? So we have the Ex and Hy components which are traveling in between the two conductor plates. This is Z, this is X, this is Y. So suppose I have this Ex, or rather let us say Hy, which looks like this. The wave is traveling this way, and the electric field vector is over here. It is along the x-axis. So it is traveling along the plus z direction, where Hy is obviously along the y-axis, vertical to the plane of the paper. But now what do we see? Mathematics tells us by substituting m equal to 0, we can still sustain some fields. Now let us look at the physics angle of it. So if now this wave is grazing any of the surfaces, what's going to happen? The Ex is going to be a normal electric field with respect to the surface, and the Hy is going to be a tangential field. So a normal electric field Ex will cause surface charges in the conductor, and the tangential magnetic field Hy will cause those surface charges to move, resulting in a surface current. So therefore the boundary conditions will be very well satisfied even with the fields in the in the dielectric being non-zero. So here we see boundary conditions. The boundary conditions are satisfied even with fields not dying out. So let's say how the boundary conditions are satisfied. So Ex, which is the normal E field, it gives rise to surface charges. Let's call this as rho s, and the Hy, that is the tangential H field, that causes those surface charges to move, resulting in surface current Js. So therefore the boundary conditions are very well satisfied. So there is no question why the wave cannot exist this way. So now what is more important to note here is that this wave would have existed even without these two conductors. This wave would have existed even without those two conductors. So it's like saying these walls, these conductor walls, are not playing much of a role anyway. So it's almost like saying, if you look at the expressions for the E and H fields, there is absolutely no way where the D of the conductors, or for that matter any other component like theta or anything, is playing a role. So it's like saying this is almost identical to the case as if the wave is traveling in an unbounded medium. So this is a very, very important result. So the TM0 mode can exist. The TM0 mode can exist, and it is exactly like a wave traveling in an unbounded medium. So it's as if the boundary walls are not playing any role whatsoever. Now what you notice is that the electric field, the magnetic field, and the direction of propagation of the wave, they are all mutually perpendicular to each other. So this TM0 mode is also called as the TEM mode, or the transverse electromagnetic mode. And this is almost identical to what we had discussed earlier, that any plane wave traveling in unbounded medium is of the form of TEM, that is transverse electromagnetic. So even with the boundary walls, the TM0 behaves exactly like the TEM. Is that fine? Now, coming back to the general case of the TE suffix small m and the TM suffix small m modes, where let us say m not equal to 0. So what we saw was, in both of these cases, for the wave traveling along plus z direction, and that is the wave which we are guiding along the structure by means of multiple reflections. So in that case, we had seen the phase constant is beta prime, which is beta times sine theta. So this is what we had proved in the last class. And so now if I say, what is the phase velocity? The phase velocity is nothing but omega by beta prime, and that is, now suppose I have a wave which is incident like this, and this wave has some velocity, let's call it as v0, that is the velocity of the independent wave. So this will be, you can just simplify, you will get this equal to v0 by beta sine theta, sorry, omega by beta sine theta, and omega by beta, that is equal to v0, that is v0 by sine theta. And if you want to remove the sine theta, you can simply put v0 divided by 1 minus m lambda by 2d whole square. So the phase velocity Vp of the wave that is traveling along the plus z direction can be more than v0, as is the property of phase velocity. So what about the group velocity? What about the group velocity? That is Vg. So essentially, this Vg, if this is theta, the component of this theta, or the component of this V0 that is appearing across the z direction, the plus z direction, is nothing but V0 times sine theta, and that is V0 into 1 minus m lambda by 2d whole square. So that is how it is. Now, what do we notice? What do we notice? What we are noticing is that in general, for m not equal to 0, for any mode m, for both TE and TM, for both TE and TM, for m not equal to 0, the Vp and Vg, the group velocity and the phase velocity, they depend on a lot of things. They are functions of lambda, they are functions of the mode m and also of d. So if they are dependent on lambda, obviously they are dependent on frequency. So any means of propagation where the velocities are different depending on the wavelength or the frequency, they are called as dispersive modes. Dispersive mode of propagation. That is like saying when a ray of white light tries to pass through a glass slab, it splits into its constituent colors because the speed of the wave in the medium depends on the wavelength. So therefore, there is only one mode of propagation which is non-dispersive, and that is the TM0. Or this is also the TEM mode. So what is the characteristic of TM0? The characteristic of TM0 is that its phase constant is still beta, and that makes the velocity equal to V0. So effectively the Vp is equal to Vg, that is equal to V0. This is the only non-dispersive mode of propagation possible in the parallel plane waveguide. All other ways in which the wave is incident obliquely on any of the conductors, they will consist of an m which is not equal to 0 because theta is not equal to 0. Therefore, they will be dispersive. So now if we try to plot a graph of velocity versus the frequency, let's say. Now let us look at what we had derived in the just few minutes back. The phase velocity looks like this and group velocity looks like this. So if I put m as 0, that is, I essentially come to the TM0 mode. What essentially happens is both phase velocity and group velocity become equal to V0, and there is no concept of frequency at all. So therefore, if this is V0, this indicates the way the TM0 mode propagates. And as you can see, any frequency, any frequency can propagate using TM0 because this is a non-dispersive mode. There is no concept of what we call as the cutoff frequency. So we had actually defined the cutoff frequencies that in the previous class, that in case of TE mode and similar for TM mode also, the frequency of the wave has to be above a certain value. So in general, f should be more than f min for any m that is not equal to 0. This is what we mean. So you can very easily prove that, let us say I'm putting some frequency here. This is, let me call this as f min for m equal to 1. Let me call this as f min for m equal to 2, and let me see what happens in these two cases. So when m equal to 1, when m becomes exactly equal to 1 and f is exactly equal to f min, if m is equal to 1 and f is exactly equal to f min, this m lambda by 2d will essentially become 1. So therefore, the phase velocity will almost become infinity and the group velocity will tend to 0. Now, as we increase the frequency, this m lambda by 2d term will start tending to 0. It will start tending to 0 because the frequency is increasing, and therefore if the frequency is sufficiently high, both phase velocity and group velocity will tend towards the value v0. So if I draw the phase velocity, when f equals f min, it is almost equal to infinity, and when f is much more than f min, m equal to 1, it is almost equal to v0. So therefore the phase velocity will look like this. It's a second order curve, so it's something of this kind. Likewise, this is Vp for m equal to 1. Now if I draw Vg, it will start from 0 and again it will go towards V0. So this looks something of this kind. Similar things will happen for m equal to 2 also. Again it will start from infinity. This is Vg, and Vg will also look like this. Right? So this is what it looks like. So this is something very interesting. So any of these, so only this straight line is indicating a non-dispersive mode of propagation. And all of these other curves, all of these, second order curves, they look like, since they are not linear, they have some cutoff frequencies below which they cannot exist. So what you will see is that these m equal to 1, m equal to 2 and other values of m, they are all dispersive modes of propagation. So we had proved in the previous class that f min for any m is equal to mv by 2d. So if m increases, even the f min increases almost linearly. So that is something very interesting. So now completes one part of the analysis of waveguides, that is the parallel plate, that's a parallel plate waveguide. So as we had discussed, that the parallel plate waveguide forms the very basic of understanding what is a two-conductor system. A two-conductor system. The simplest example of a two-conductor system is a transmission line. So if I have a transmission line, and the question now is that is there a mode of propagation in the transmission line also? Yes, there is. Although when we were discussing transmission lines, we did not explicitly mention it because we were not aware of these phenomena at that time. So now, suppose I give you this graph, the velocity versus frequency graph, and I tell you, choose the best possible mode. Choose the best possible mode. So obviously the best possible mode will be TM0, because the TM0 is the non-dispersive mode. It passes any frequency, right from DC to high frequencies. So therefore this TM0 is called as the dominant mode. Means this is the mode which can pass maximum amount of frequencies or signals. So now let us say if I have a transmission line and there is some electromagnetic field which is inside it, I want that it should travel using the TEM mode of propagation. So what essentially happens is the H field is perpendicular to the plane of the paper and the electric field is like this. So this is how it moves. So this is the z-axis. So this can definitely exist. So effectively what happens if I have a transmission line, the electric field essentially exists between the two conductors and the magnetic field tries to loop around the two conductors because of their surface currents. And this is the way the fields exist, and they come as a consequence of the voltage and H comes as a consequence of the current. So effectively, without realizing at that time, the discussion on transmission lines was largely limited to, when it travels in a transverse electromagnetic mode or the TM0 mode of propagation, the transverse magnetic mode 0. And that is valid also because we just proved that this TM0 is the dominant mode of propagation in a two-conductor system. So obviously the other means can also exist, but since TM0 is the dominant, we shall look more at that. So as I mentioned earlier, that similar things happen for other two-conductor systems, like two parallel pieces of conductors on a circuit board, coaxial cable conductors, the outer conductor, inner conductor, they obey very similar laws. Of course, the way the fields are aligned may be a little different, but effectively we can all say that in two conductor systems this can propagate. Alright, so with this we come to the end of this part of the discussion. Thank you.